Kazuki Shibanuma, a numerical simulation model of microscopic cleavage crack propagation based on 3D extended finite element model. And just that.
Thank you very much, Chairman. My name is Kishimata from the University of Tokyo, Japan. Today, I'm going to talk about the numerical simulation model of microscopic cleavage crack propagation based on 3D XFEM. This slide shows the table of contents of this presentation. First, I will show you the background and objective of this study. Preventing brittle or cleavage crack propagation in structures such as ships, tanks, and other pressure vessels is extremely important in the viewpoint of the double integrity. This figure shows the large-scale aspects in cleavage crack propagation. In this study, we focused on this one. Cleavage crack propagation in polycrystal. This is a phenomenon in microscale or semi-microscale problem. The motivation of our study is a clarification of the relationship between microstructure and cleavage crack propagation resistance. The materials development in industries has depended only empirical knowledge based on the experiments because the theoretical background of the property of the cleavage crack propagation resistance has hardly been clarified yet. One of the major reasons of this lack of understanding may be the complexity of the phenomena. As you can see from this figure, that is a 3D image of the cleavage crack surface in a steel measured by laser microscope. We can see so complicated fracture surface formation from this figure. So, the cleavage crack surface in VCC solids, including steels, is composed of two kinds of fracture surfaces, cleavage planes and tear ridges. The cleavage planes are formed on the boundary plane of the respective grain, and tear ridges are ductile fracture surfaces formed in the gap of two cleavage planes along the grain boundary. The area of the tear ridges formation is decided by the cleavage plane formation from this one. So in this study, we focused on this cleavage plane only. Due to so complicated 3D fracture surface forming, there has been no model for accurately simulating this microscopic crack behavior. On the other hand, in fact, this phenomenon does not have strong material and geometrical nonlinearities. So these features indicate the applicability of the extended finite element method, XFEM. So I will show you the model development. This slide shows a modeling concept. The most important point of our model is that polycrystal, including geometries and orientations of respective grains, is defined independent from the finite element mesh. These are connected by crack shape. The relationship between the crack shape and polycrystal is, of course, a cleavage plane formation. And that is, the crack shape crack is formed in respective grain, on respective under plane of the grain. And on the other hand, the relationship between the finite element mesh and the crack shape can be expressed by enrichment, which is a special approximation in the extended finite element method, XFEM. The XFEM is short for the extended finite element method. The XFEM is a kind of FM, but no need to remeshing for crack propagation analysis. So crack can be modeled independently from finite element mesh. The approximation of the displacement field in the XFM can be expressed as by the additional nodal degrees of freedom and the interpolation functions near crack, like this expression. This first term is the standard finite element approximation, and second term is enrichment. We employed two kinds of enrichment functions. The first is a Heaviside function to express the crack discontinuity as expressed like this equation. And second enrichment function is so-called branch functions to express the asymptotic field, crack tip field, expressed as this equation. These enrichment functions are the same ones in the original XFM formulation proposed in 16 years ago. Yeah. As a stress intensity factor evaluation, we employ the interaction integral method, which is J integral based method to separate stress intensity factors of respective fraction mode. But in fact, the numerical accuracy of the interaction integral method strongly depends on its implementation scheme. We employ the implementation scheme proposed by Gonzalez et al. In 2013. Their scheme show the best performance in the range of our knowledge. And polycrystal generation was conducted by the NEPA, which is an open software to generate 3D polycrystal based on Voronoi diagram. And the NEPA can reproduce the grain size distribution with proper geometry. And this software NEPA have a function of the finite element mesh generator as well, but we didn't employ it because in our model, polycrystal can be defined independently from finite element mesh. The cleavage plane in BCC solids, including steels, is formed on 100 plane of the grain, like this. This is the main reason of the complicated fracture surface morphology. But on the other hand, during the cleavage plane formation, there may be not strong material and geometrical nonlinearity. So this feature of the phenomena indicates the availability of the advantage of the XFM. As a fracture criterion, a cleavage plane is assumed to be formed on the one of the planes where the maximum normal stress is applied. Like this. Maximum normal stress is applied under the plane. So the maximum normal stress can be calculated from the respective stress intensity factors and the grain orientation in front of the crack tip. In addition, the evaluation point is assumed at the center of elemental crack front, and crack propagation is assumed to occur at the evaluation point having the maximum value of the normal maximum normal stresses. So crack propagation can be simulated step-by-step calculation. Next, I will show you the model validation. It is difficult to measure the microscopic cleavage crack propagation directly, so the validation was conducted by fractography. This slide shows the employed test tubes. We employed ordinary ferrite steel, which is most widely used as the structural steels. Optical micrograph, chemical compositions, and grain size distributions, and tensile properties. The average grain size is about 20 micrometer, and yield strength is about 320 megapascal. In order to obtain the fracture surface, we conducted DCB test. Using machined observation samples from the fracture surface, we conducted two kinds of validations. The first validation is for the crack propagation path. In ordinary SEM observation, we can estimate the crack propagation path by following river patterns on the cleavage planes, like this. That is a kind of qualitative evaluation of the microscopic crack propagation behavior. The second validation is for the cleavage plane directions. Using the results of EBXD analysis for the cross section like this, we can obtain the grain orientation of the cleaved grain. So, compared with the high resolution SEM image, we can identify the one of Wanderser plane from the three candidates of the Wanderser planes of the respective planes. So, we can obtain the distribution of the cleavage plane directions in 3D. So that is a kind of quantitative evaluation of the cleavage plane formation. This slide shows an example of numerical simulation of our model. The domain size was 200 micrometer cube, and the total number of finite elements was 69,000.
2 more minutes, please.
2 minutes? Oh. Oh my God. Okay. And what's this? So yeah, this slide shows the first validation results. In the CM image, we sometimes observe like this, such wrap around the behavior of the crack, like this, wrap around behavior. And this figure shows the numerical results of our model. This result shows our model shows a qualitatively good agreement with actual complicated crack propagation behavior. And then this slide shows the second validation results for the cleavage plane directions. That is much more important than the previous one. And this graph shows the cumulative probability of the normal vector component of the cleavage plane directions. We can see that the ny, the component ny, keeps the lowest values compared with other two components. It means the component ny, vertical direction of the macroscopic fracture surface is concentrated in unity. In addition, we can also see that the component nx is slightly lower than component nz. That is actual observation results. And this is model simulation results. This results, we can see amazingly good agreement with actual observation results. That result was beyond our expectation. So anyway, we can see that the quantitative validation of the model, including assumed fracture criteria, based on the maximum normal stress on the Wanderser plane. Finally, I will conclude this presentation. In this study, we developed a model for simulating microscopic cleavage crack propagation in steel based on XFEM. In the model development, polycrystal geometry was modeled independently from the finite element mesh. And the cleavage plane was modeled as one-zero plane where the maximum normal stress is applied. The validation was conducted by comparing with observation on actual fracture surface, complicated crack paths, and distribution of components of normal vectors of the cleavage plane was successfully simulated by our model. This is the end of my presentation. Thank you very much.
Thank you.